Thanks. Hi, folks. Yeah, I've been working on the various incarnations of Xeon PHI since it was called Larrabee in 3 different groups at Intel. So this has been about this last 7 years of my life, something like that. My current position is in data center group, which is the group that's responsible for all of the Intel server business, and in particular enterprise and government, which includes things like Argonne. And our particular team is called HEAT, and I forget what that stands for, but we do code modernization and tuning and performance analysis, and it's actually a fantastic team. Mike DeMello is on the team. You know him there at Argonne. So, okay, let's see. And now I'm in completely the wrong window. Sorry. There we go. This is the marketing, cartoon of the chip, if you like. I won't spend a lot of time on this, but for those of you who don't live and breathe Knight's Landing, it's nice to have a little refresher. So you can read the speeds and feeds there. It's the first Intel chip with AVX-512, which is the 512-bit AVX instruction set. Will be present on upcoming Xeon product lines, but right now the only released product that has 512 is Knight's Landing. Another unique feature is the on-package MCDRAM, which has something like 5 times the bandwidth of DDR. So those are the other thing to note here is that you've got a large number of relatively small cores. They're based on an Atom core. They do have, unlike Knight's Corner, the previous version, they are out of order. They do support out of order technology. They're 4-way threaded. They've got 2 VPUs. So there's a lot of horsepower there, but they are not nearly as big, if you like, in terms of out of order depth and ILP and issue rates and so forth as Xeon. And so that's something you have to keep in mind when you're porting code or tuning code for Knight's Landing. I don't think I'll say anything more there. Some of it will come up. This second slide also is, let me do a quick time check. So are we going to 9:30? Is that my stop time?
We have over an hour, available, so it's not fixed. We have some flexibility, but yeah, the general plan was to have about 30 minutes of talking and interleaved with possibly 30 minutes of discussion.
Okay, since we started a little late, I'll shoot for 9:30, and that'll be about 25 minutes. I think that'll be about right. Okay, so I'm not going to read this slide to you. It's really here mostly for reference. But this next slide, slide number 4, is carries some points that I'd like to make. Xeon has fewer cores at a higher clock rate with a large shared L3 cache, but less memory bandwidth, and in this generation, less flops because it's only 256 bits wide. So the way you get performance on Xeon Phi is by using all of the cores. Otherwise, you're not going to get this. Otherwise, you might as well stick to a Xeon because you won't be able to get the full flop rate. So you see that very last line there. The peak flops are way higher on KNL, but in order to get those, you have to have all of the cores doing useful work all of the time or most of the time. And that's sort of the goal of optimization. So this is sort of the outline of the talk here. I'm going to tell you about how to optimize your code to get peak throughput, and how to analyze your code to find out where it's not getting peak throughput. Or at least I'm going to give you some ideas that you can use, hopefully, to get that way. So obviously, the goal is not attainable. There's no way that every instruction in your program issued by every core on every cycle will retire 2 VPU ops. But if you want to get the peak flops or the peak SIMD throughput on the machine, then you have to get that. So when you fall short of that, then the question is why, and what can I do to fix it, and how close am I to what I can possibly get. So I'll talk about all of those things going forward. By the way, it's okay with me if somebody wants to stop and interrupt, and I can stop anytime. I will ask specifically for questions on slides that I think may be difficult or might raise some questions. So for now, I'll stop for 5 seconds. Are there any questions at this point? Okay. Slide 6. So peak throughput is 2 unmasked full width SIMD instructions retiring every clock. What are the things that might prevent my program from getting there? Parallel scalability is clearly important because I need to use all the cores all the time. The parallel scalability impediments may be due to algorithmic issues. For example, you have a lot of true dependencies in your code, which require that you synchronize threads or MPI ranks. And there's not anything you can do about true dependencies except change your algorithm. So we're assuming, so your algorithm may be synchronization, may have a lot of inherent synchronization, or it may not. But synchronization is one of the impediments to parallel scalability. What I'm trying to do here is just kind of come from 10,000 feet. So you start with a program. It's only getting 40 gigaflops per KNL node, and you need to know why. So from a top down, well, it's either because it's not using all the cores, or it's not using them all well, or it's not using enough memory bandwidth, or any number of things like that. And so if you break down the process of analyzing your program into seeing what the impediments are to peak throughput, then that'll give you sort of a framework to hang your analysis and optimizations off. So if you've got algorithmic issues with load imbalance or synchronization, that includes serial time, Amdahl's law. Architectural impediments, things your program isn't necessarily doing, but is causing the microarchitecture to behave badly. For example, fault sharing, or true sharing would be synchronization. False sharing would be kind of cache contention that you might be able to avoid. You might be limited by the interconnect. And again, there may not be much you can do about that, but it's nice to know. And of course, you may be memory bandwidth limited. And that's probably the first thing to look at in most HPC codes, especially PDE types of codes. And this analysis, this talk is mostly about single node performance, but all of these metrics apply to distributed memory and shared memory kind of equally. You've got interconnects that can be a bottleneck. You've got synchronization that can be a bottleneck, that sort of thing. So that's the parallel issue. So, and then secondly, how well am I using the core itself? And remember, I want to retire 2 AVX-512 instructions per cycle. So if I'm not vectorized, then I don't have AVX-512 instructions, or I have AVX-512 instructions that only operate on one element. So you might have algorithms that aren't vectorizable, or aren't vectorizable in the way you've presented them. Got ISO limitations. For example, Knight's Landing does not support AVX-512 operations on bytes or 16-bit words. So you need to have 32 or 64-bit data types. Otherwise, the compiler will not be able to generate code because there's no code to generate. And you may have compiler limitations. The compiler may not be able to vectorize a loop for one reason or another. The compiler, go ahead.
Excuse me. Would you expect the compiler to promote those smaller types?
Well, it depends. Yes, in many cases it will, but and that may or may not be the most efficient. So for example, that's actually a great question, and I would have to check, but I'm pretty sure that if you had, say, 16 bytes, you were doing something on 16 bytes, then the compiler, I think, will promote that to 32-bit values, but I'm not absolutely certain about that. It's something to watch for, and you'll see that we have an optimization report that will tell you whether the compiler is having an issue with that kind of a loop.
So
But
I
it
guess
is a loop. Yeah. Go ahead.
I guess it's
Sorry.
implicit for most of these purposes that we're talking about the Intel compiler.
Yes, we do enable support in LLVM and in GCC, but the Intel compiler will be better, and that's the one I use pretty much exclusively, unless there's some customer need to try a different compiler. Okay. So the other thing I don't talk a lot about here, but is very important, is you can add directives to tell the compiler for things it can't figure out in loops to help it vectorize, and that's a talk unto itself. Finally, if you have loops with a lot of if statements, so that different lanes of the SIMD are working on different data, you can end up with very sparse masking. So a lot of, and you can end up with what ultimately the compiler may think it's vectorizing, but ultimately you may only have one bit set in the mask for a number of the instructions and only one SIMD lane active. So that's something that you can often improve by changing your code. And again, these are I'm trying to give you kind of a high level. These are things to look at rather than a sort of a 4-hour training class on optimizing your code. Okay, so big cores versus small cores. All of this stuff helps Xeon as well, clearly, because Xeon still has a lot of cores and synchronization still matters and all of that. So you're not doing the work only for Xeon PHI. You should get improvement across Intel's server product line. And as we go forward, every generation of Xeon has more cores, and AVX-512 will be in the next generation of Xeon. So you'll get that for free, more or less, if you do the work for Knights Landing. Most of the performance issues will occur on both, but they can be exacerbated by the many small cores on Knights Landing. So you know problems in your code that won't show up on Xeon may show up on Knights Landing. Two other things: memory is of course always a critical issue, and missing the large L3 can have pretty serious effects one way or the other between Xeon and Xeon PHI. To compensate for that, Xeon PHI KNL has the MCDRAM. So if you can use that effectively, then you've got 5 times the bandwidth you would have otherwise, and close to, not 5 times the best Xeon bandwidth, but substantially more than the best Xeon bandwidth, especially on a single socket system. It's in the neighborhood of, I think, 80 on Broadwell right now for a single socket. Let's see, 920. Okay, so specific optimizations for Xeon PHI. For bandwidth bound problems, use MCDRAM. And we could spend a lot of time talking about MCDRAM, maybe in the session in the question and answer at the end. There'll be some questions about that. I have one slide on it later. But the 10,000 foot view is MCDRAM gives you almost 500 gigabytes per second, and DDR gives you about 90, 95, something like that. 90, I think, is peak. Latency hiding is important on Xeon and Xeon PHI, but it's harder on Xeon PHI, and there are a couple of mechanisms to use that aren't usually used on Xeon. So out of order, you've got some latency hiding already, but the out of order window is only 72 microops. What that means is that that you can have up to 72. You can think of it as 72 instructions. It's close enough, except for some weird instructions. You can have up to 72 instructions all in the processor at once, and it will retire those as the resources become available. But as soon as it tries to issue more instructions, if those 72 slots are full, then you'll stall. Whereas on Xeon, you've got many more. That buffer's much deeper. It's probably at least twice that, I think. Probably more on modern Xeon. However, to help make up for that, we do have up to 4 hyperthreads per core. So each hyperthread has its own set of registers, its own context. It's really a hardware thread context, but it shares all of the core's resources, all of the caches, and all of the execution pipeline. That means that when one hyperthread can't issue instructions because of some stall, another one might be able to issue instructions. So it's a way to keep the core's internal pipelines full by using multiple threads. And sometimes you can use a technique where the kind of think of it as the outer level of parallelism is across the cores. And so you block your algorithm to a L2 friendly size, actually even across the tiles, which is 2 cores. 2 cores share an L2 on Knight's Landing. And then within those tiles, you have the hyperthreads on the core or tile cooperating on the shared data and cache. And there's a number of papers and things on that. And then finally, so latency is, if latency is due to memory, which is really usually the biggest issue, you can insert manual prefetches, or you can have the compiler try to insert software prefetches. And this is a key tuning thing for Knight's Landing. It's a pain, but in key kernels, it can make a big difference. And again, the compiler can do it and sometimes do a good job, and you won't have to do it. The other area of optimization for Xeon PHI that's critically important is vectorization. What's different about Xeon PHI for Xeon? Well, number one, we've got AVX-512, although that will change with Skylake. So it's a much more efficient instruction set than AVX2. But specifically on Xeon PHI, we've got some special instructions for HPC, faster, exponential, and reciprocal. And there's some compiler switches that will have the compiler select for those. Also, non-temporal stores, bypassing cache is really important for streaming type codes. Again, that works on Xeon, but it's not nearly as important. And then another new thing, which is another talk in itself, is conflict detection. So with AVX-512, there's a conflict detection instructions that allows the compiler to vectorize loops that store where multiple lanes might store to the same memory location. So here, these are things that are specific to Xeon PHI versus Xeon. Questions at this point? Slide 8. Okay. Here's an example of what you can do by applying these optimizations. We started with this QCD code that Dr. Ishikawa in Japan wrote, and he had done it for Knight's Corner, and he had done a lot of work. He had written everything in intrinsics. The QCD guys are crazy, and so this is all hand code. It's generating really nice assembly language, but it was running really badly. So I came in and did these kinds of optimizations. I did this for Knight's Corner, and then when Knight's Landing came along, I did the same thing for Knight's Landing. And so starting with a very highly optimized, very good assembly language, he was still getting bad performance. And the things that I helped him with to improve the performance, well, on Knight's Landing, it's a bandwidth bound problem, so we get to use the MCDRAM. And you can see in the table at the bottom that MCDRAM alone makes a huge difference. Tiling for cache, I don't have the before and after, but that was something I did for Knight's Corner. Manual prefetching, you can see again that makes a pretty significant difference in the performance with and without manual prefetching. He'd already done the intrinsics, aligned memory allocation, cooperative threading, the 2-level threading I was talked about. So we kind of start from on DDR only with with this really nice code. You're only getting 100 um, gigaflops on the full solver, and then after you use high bandwidth memory, that alone gives you this sort of 3x improvement. But then you get another 30% by adding software prefetching. And this is on top of all these other optimizations. This is what we sometimes call ninja code. I wouldn't expect everybody to do this, but it gives you an idea of what you might be leaving on the table. Let's see. I think okay. So now I've got my program running. I want to know how good the performance is. How do I analyze the performance? I mean, I'm sure you all have many different ways of doing that. I'm not telling you to stop doing that, but here's what I do. Um, I use these hardware events, which are all available, and I'll just let you read these. But these are the kinds of things that you can fairly easily determine how well the core is doing. Are you missing cache? What's my memory bandwidth? That sort of thing. I use Vtune. Linux Perf is good. I find that Linux Perf on KNL, especially for when you're running lots and lots of threads, can be more intrusive than Vtune. So I mostly use Vtune, but I use Perf on occasion as well. And then most of these third-party tools, and I'm not familiar with Craze tools, but I'm pretty sure they all work on KNL as well. So that would be something. Have been ported to KNL. But really, regardless of what tool you use, what you want to find out is how well is the core doing. So here's some things that give you ideas of how the core is doing. So the best you can possibly do is to retire 2 instructions per cycle. Vtune shows you the reciprocal of that, which is cycles per instructions. And the whole point of this slide is that cycles per instruction per core is the measure that you want, but the measure that you get is cycles per instruction per thread. And so you need to know how many hyperthreads you're running to know how close that is to the maximum. So you either, depending on whether it's the reciprocal or the other, you either multiply or divide by the number of threads per core that you are running at the time. And here's what you get now. I realize that this is what I do. I run Vtune and I get hardware hotspots, and I just look at the breakdown in module, and this immediately tells me that I've got all this spin time because I've got all this time in OpenMP. I realize that this doesn't work on Cray because Cray statically links by default. So you can use the same method, but you end up having to look at the individual functions and guess whether or not they belong to your program or to the runtime. And that's usually not too hard. It makes it a little more tricky. So all of this works. And then after I did this slide, I said, oh, wait, this is Cray. So I apologize for that. But what you're seeing by looking at this is that in the solver itself, my CPI seems kind of high. I would like that to be, I know I'm running through 2 threads per core, so I'd like that number to be 1, and instead it's 2.4, so that gives me something to look at. It turns out that that's actually good, but you have to do more analysis to figure that out. But if you're just looking at it from scratch, that's the first thing I'd look at. And then I'd look at, I don't care what the CPI is in OpenMP, because that's not doing useful work. I only care how much time it's spending in that. So I would start looking for serialization and load imbalance at that point. And then kernel time is okay here, but sometimes kernel time can be really high, and that's a whole nother thing you have to do. I just said all of this, so I'm not going to read it all to you, but this is mostly what I said. Look, figure out where your code should be doing useful work versus where it's spinning. When you're optimizing the useful work, look at CPI. When you're optimizing the spinning, look for load imbalance and serial time and other synchronization. Here's some tips on using Vtune. A lot of people use Vtune the first time and say it sucks, and I don't blame them. It does not handle very long runs, especially on KNL, very well. Because there's so much data and because the processor is slow relative to Xeon. And so it's best to target your Vtune collection to a chunk of the code. And some of the other tools may not have these limitations, but I don't know that they give you the same kind of very fine architectural level breakdown of cycles that I can get from Vtune. There's also some built-in analyses that will help you. You know, you're not an expert on the hardware counters, and it will help explain to you where your code is bottlenecked, general expiration, or how much memory bandwidth it's getting with memory access, and what your L2 traffic looks like. Let's see. You can also instrument your code by hand. This is getting into somebody who really wants to dig into the lowest level of their kernels, library writers or QCD people or me. And there's a bunch of different ways to do that. I won't read all of this in detail, but there's lots of resources. And here's an example of some of the metrics that you might compute from that. So for example, I did this on QCD. I read the counters inside the code itself and then had, you know, Python and spreadsheets and computed all this interesting stuff. I've got, here's L1 here. Now Vtune will also give you these metrics if you collect with memory access, for example. It presents them slightly differently, but it uses more or less, and it'll tell you how it computes everything. L1 hit rate, L2 hit rate look quite good. IPC per core is 1.16, which is, you know, it could be as low as 0.5. But then when I look at the last two rows, I see that my MCDRAM read bandwidth is 317, and my peak read bandwidth from MCDRAM is 360. So I'm pretty close. And in fact, then I look at my L2 input bandwidth. How many L2 lines per aggregate? What does that translate to in terms of bandwidth? And that tells you how busy the mesh is. And in fact, that's 341 gigabytes. I use 360 as a rule of thumb. So you know, I won't say that I can't make this code run faster, but I know that I'm definitely at the point of diminishing returns, even though I'm only getting 1.16 IPC. See, here's how you use MCDRAM. You may already know this. If you don't, we can go into it in the Q&A or separately. You can use the MCDRAM either as a separate NUMA node, which is 16 gigabytes of memory, and you can tell the OS to use that. You can use cache mode, which backs, so DDR is, MCDRAM acts as a cache for DDR that has advantages and disadvantages. You can also explicitly allocate, and we have an API for that, if you have some data structures that you know need to be in MCDRAM. And Vtune has some things that might help you to find the data structures that you should put into MCDRAM. Compiler opt report, if you haven't seen this, you should. I know this is an eye chart, but I highlighted some of the interesting things. This is from WRF, big Fortran code. It vectorized this loop. I had to tell it SIMD because of the potential data dependencies in the I dimension in those if statements down at the bottom. It turns out those are in fact not real dependencies, and you can prove it if you stare at it long enough. So SIMD tells it, ignore that dependence, and then it tells you a bunch about what it did. Let's see, and then how do you know when you're done? I kind of told you that for CCS-QCD. If you're using all of memory bandwidth, that's good, but you might be using all of memory bandwidth unnecessarily. If you haven't tiled for cache, you might be rereading the same data over and over again. So you need to make sure that just because you're using a lot of bandwidth doesn't mean that you're using it effectively. And then IPC. And of course, those have to be useful instructions. So only look for IPC in the useful parts of your code. And even if you're getting really good IPC, if they're scalar instructions, then you're not getting a lot of flops. ultimately, when you kind of get the memory fixed and all of that, then you'll hit the point where you might start hitting microarchitectural um, limitations or real dependencies, and then it gets very problem specific and loop specific and requires deeper knowledge. But you can go a long way just by fixing the memory and getting the compiler to vectorize as much as it can. And I would say that for most codes, that's sufficient. Here's a bunch of resources. Some of these, I think they're a little old, but they should all be correct. My goal in this talk was to whet your appetite, to tell you what some of the tools are, some of the places you need to look. We have tons more stuff online, and you can spend as much time as you want learning this stuff, or as little as you need to. That's all. Sorry, I went a little over.
Oh, that's no problem at all. So I think that I can unmute everyone. I think a few people are administratively muted now, but just if you're not talking, could you mute? Could all the participants, can you mute on your end unless you're talking?
I believe I have to stop sharing my screen in order to see everybody. But for now, I'll just leave it up.
Richard and Vitali, you're not muted on your end. I muted you from this end temporarily. So we would be great to discuss anything that Larry brought up.
But one question I had is just sort of about the typical applications that you see. How often is it that people have actually done manual prefetching, and are there examples out there people could look at?
Yeah, you mentioned it was a ninja code.
Hey, before you guys go on, if you ask a question, could folks say, "Hey, this is so and so from so and where," just so that we can know what's going on. Thanks.
Yeah. Hi, so this is Tim Williams from Argonne.
Right, and just for those of you who don't know me, I'm Ray Loy, also from Argonne. Oh, Larry, I think you're muted.
You're right, I was muted, sorry. I would say that 95% of the applications don't have manual prefetching. I really don't think you have to go there too often. Certainly, if you're doing libraries, for example, Jongnim Kim and Amrita Mutharia, sorry, I need her last name in front of me. In our group, I know they've presented to Argonne a couple of times, and you guys know Jongnim for forever. But they've done that in QMC Pack. So in that kind of thing where you've got code we do it in MKL. I think that's really the place for it. QCD guys are nuts, like I said. So.
All right, thanks.
Yeah. The compiler is getting better at it too. It's not on by default for Knight's Landing though. So that's another thing another talk in itself, I think.
And so this is Tim again. One other sort of general question that I've had asked to me once or twice is just generally, if I come in, if I've tuned well for threading on the node,
yeah. Mm-hmm.
Is it typical that that's completely orthogonal to the use of SIMD, so that I can then go in without having to change my parallel loop control and and put SIMD in at the appropriate loop level.
Yes, in general, I would say that's true. What you will find is that the balance will change substantially as you get more vectorization, especially if you have none at all. And so if you may see, typically you'll use a lot more bandwidth. And so if you were seeing threads scaling and then you have SIMD and the threads don't scale anymore, definitely look at memory bandwidth because you're probably using a lot more of it. But the threading itself, if you've taken care of minimizing synchronization and load imbalance and so forth, hopefully that would stay the same.
I mean, have you seen? Have you seen cases? You referred to the balance. I could see a situation where at the thread level there might not be enough work to vectorize, so that you might have to push everything up one level. Have you seen cases of that?
Certainly in codes with a lot of indirection, right? They don't vectorize very well. And so can you vectorize outer loops, that kind of thing? Is that what you're talking about, or?
Well, if a single thread, so you come into this and let's say it's a threaded code, but it's not, nobody's paid attention to vectorizing at all. Right. And so your threads, maybe it was sort of at the thin end of being threadable. There isn't that much work in a thread, and so you might need to lift up the distribution between threads and to do the vector.
Yeah, we see that. Sure. It's easy to scale if you start from slow code, right? So.
And that's where I guess if suddenly if vectorization comes in and it makes a big improvement, then maybe I don't scale out to as many threads anymore.
That's right, and then you got to look for the next bottleneck. I mean, it's very iterative. I would have liked to have emphasized that more in my presentation, is that you find a bottleneck, you fix it, suddenly everything looks different and you have to go back through it again. But hopefully the general time to solution line goes down. It's just the internal details change.
We have a question from Will about which versions of iFort. I think he's asking about which versions of iFort support the flags for the compiler reports.
Well, we've had compiler reports forever, but the current version is 17. I think from 16.4 on, but certainly in 17.0 and upcoming 17.1, the op report is much better. But there's been the op report flags have been there for 2 or 3 releases, but they change in every release. So I recommend you use compiler 2017. It's much, much better than it was in, say, 2015.
It's 17 has all of the KNL specifics in there now, I guess.
Yes. Yeah, they've been in since 2016 U3 or 4, but I can't remember when they changed the op report.
Version 14 onwards.
14? Was it that long ago that they did the new one? I mean, the new op report is head and shoulders above what it used to be. So just use the latest and you'll be much happier.
It's been evolving.
So we're also very interested, besides discussing this topic, whether you have any thoughts about both the format of this kind of talk and topics that you might be interested in the future. I can see already that a more in-depth discussion about memory usage might be a good follow-up topic. So whether it's during the discussion or you send us a note later, it would be great to get your feedback about those issues.
We'll also be sending out a survey in the next week or so, because we're also looking for ideas on what you guys want in future versions of this talk. The goal here is to create dialogue between all of you and someone like Larry here. The goal isn't to recreate more webinars. So we strongly encourage you to speak up and turn on your video like me and ask questions of the people that we're bringing in. We're also looking for who we should bring in next. So those things are on the table. And we have 12 more minutes, so feel free to jump in and don't be shy. It's a small crowd.
Larry?
Can you hear Mike, Larry?
Yeah, sorry, I was muted again. Go ahead.
Okay.
Could you say a few words about the CPI per core versus CPI per thread?
Yeah, that was an issue. That's when you guys helped me when we did the run through, and I added that. Let me find that slide. Just a second. My colleague. I wanted to emphasize this slide. Thank you for that opportunity. So again, hardware architects say IPC. Vtune chose to use CPI. I don't know. You can choose. So IPC is limited by 2. CPI is limited by 0.5, but has no upper limit. So that should be clear enough. And you just count that as how many instructions. There's 2 hardware counters. How many instructions were retired and how many clocks were executed while retiring those instructions. Now those counters are per thread. So each thread has its own instructions retired. And so you get, if you compute this metric using the hardware counters, which is what Vtune does, then you get per thread CPI. But if you're running 2 threads per core, each of those threads is retiring instructions at the same time. So in other words, those CPU clock unhalted.thread values overlap. They refer to the same time interval. And therefore, if you take the sum of them and the sum of retired, sorry, if you if you take the so each thread is retiring instructions at the same time, which means that the per core IPC is twice what it would be. If there's 4 threads, it's 4 times what it would be. Does that make sense? And then CPI is the reciprocal, so you divide instead of multiplying because smaller is better. So, and your real metric is threads can't retire instructions. Only cores can retire instructions. And so you really want to know how many total instructions did the core retire over this time interval, and you get that by taking the IPC and dividing by 2 or 4. Sorry, multiplying by 2 or 4.
Thanks.
Yeah, it's really easy to get confused. And Jason, and this is, sorry, and then I wanted to make my other point. See that little note that says this is why all scaling graphs should be in terms of cores, not threads. So I see graphs all the time that say, okay, I ran my code from 0 to 255 threads, and here's the scaling. So it goes up to 64, right? And then it drops down really badly. And then it goes up again to 128, and then it drops down again, and then it goes, and it's just, and I don't understand why this graph is so weird. Well, it's because threads are not all equal. It depends on how many there are per core. And so So you should always use the same number of threads per core, and you should always show graphs with 1, 2, and 4 threads per core if that's what you want to show. But you should never go show graph. Yeah. Go ahead.
So you're saying in that graph, the threads were laid out breadth first instead of depth first?
Sure.
Something like that. Yeah.
Well, that's right. So if you normally what will happen is that you have a round robin distribution. So you'll get from 0 to 64 you'll get 1 thread per core. And then with 65 you'll have one with 2 threads and the other 63 with only 1 thread, and so
exactly what I was saying. Yeah.
Now you can change that, and in fact I have a whole another presentation and some stuff I'm working on. It's really easy to tell Intel OpenMP to use 2 threads per core. And if you just do that, then you don't have this problem. But you still have the issue in how you present the data, where you really want to show cores as the unit of scale. And that's true on Xeon too, but nobody ever uses more than 1 thread per core on Xeon, or hardly ever. And so it doesn't show up. Anyway, that's my pet peeve.
And Larry, do you recommend the KMP affinity environment?
Well, so so I like KMP affinity, but it's not standard. So I recommend using it anyway, especially if you're not using nested OpenMP, which most people are not. Then KMP affinity equals 2C is the default I would use. So KMP hardware subset, KMP HW subset equals 2T. Will give you 2 threads per core, no matter how many, and it works fine with MPI. So if you're running 4 ranks, you'll get, 64 divided by 4 with 2 threads per core, 16, that sort of thing. It just works. But if you're using nested OpenMP, it's harder. And then you need to use OMP places and OMP num threads with multiple dimensions and so forth. I've got a document written up on this, but I haven't. I have to figure out how to. And I've got even a little GUI that tells you what to use depending on how many MPI ranks and so forth. But I haven't figured out how to distribute it yet.
Little calculator.
Yeah, well, exactly. It's like a lone rate calculator. You fill in the parts and it tries to fill in the rest. It's the only first JavaScript program I ever wrote. It's really terrible. Getting better, though. After the 6th time, it started to look sort of okay.
So are there any additional questions for Larry or topic requests for the future?
I mean, we could, I don't know how we give classes on this stuff. I mean, there's a whole lot of, there's hours and hours of material here, but that doesn't really fit your sessions, I guess, unless you wanted to deep dive into something.
Well, we also have, we're also releasing on a regular basis some of these training videos that people can take a look at. Yeah. So there was one sent out last week. Yeah. So.
I mean, I could, one thing that I have a love-hate relationship with Vtune, and I know that a lot of customers just have the hate part. And I'd really like to, if one thing I could do if people were interested is, give you an online demo and show you, okay, this is how I use it. This is how you avoid the pain. And so anyway, that's one possibility if it sounded interesting to customers.
Uh-huh. What do people think about that?
I think that'd be great, Larry, but I'm not one of the ESP members. So what we can do is we can mark that down as one of the topics that we could send to people out saying, Would you be interested in this? But I definitely think that would be great, because a long time ago I used Vtune, and like I got a little ways there with it, and then I got super frustrated and totally gave up.
Yep, that was my first experience too. Since I was actually on the Vtune team for a while, so I think I have both paid my dues and contributed a lot to the improvement. Although I think it's head and shoulders above the rest, and if you avoid above the way it used to be. Sorry, I don't mean above the rest of tools. And if you avoid the pain points, it's really quite nice. But even folks in my group, are constantly bitching about it. I say, well, you're not doing it right. Oh, gee, I didn't know that, or whatever. So.
Well, it sounds like you've got a couple of talks already lined up for us, so that would be great. Thanks.
Sure. Yeah. Well, far be it from me to say you shouldn't use other tools. So if somebody else wanted to give a talk on, other tools that they use, I'd love to watch that talk. But anyway.